Alright, good evening. Welcome to Lecture 3.1 of Unit 2, Quarks and Leptons. Here are your learning intention and success criteria. Please pause the video and complete the knowledge and skills table. Okay, now one of the things we can see when looking through here is that the cognitive verb load is very simple. You need to recall and describe and define. So everything here is coming under the knowledge table. A couple of things: you need to know what these fundamental particles and antiparticles are. We need to know the definition for this. And we need to know what are quarks, leptons, baryons and mesons. Recall slightly above define in that once you can define what a quark is, you need to know what the 6 types are, same with a lepton there. Okay, now, in the 1900s, we thought physics was basically done. Atoms were made up of protons, neutrons, and electrons, and that was it. These were our fundamental particles. So the definition we gave for fundamental particles, or an elementary particle, is a particle with no substructure. So it's not made of anything smaller. Originally, the Greeks thought this was with atoms. They said, yep, atoms, they're there, they're fundamental. Well, then the idea was forgotten for a while, then reinvigorated. Then they started probing the atom, and they discovered, oh no, it's made of these smaller bits. So then the question was, well, are they made of smaller bits? And they kept testing, they found out, yes, protons and neutrons are made of smaller bits, but electrons are not. So that gave us this idea of fundamental particles, something that is not made up of anything else. And so far we think the limit is quarks and leptons. Perhaps there might be something down the track we discover, but for now this is the point. But antimatter is a bit of an interesting one. Now, in 1928, Paul Dirac was working on a version of the wave equation, and this is what he came up with, which is very, very complicated. But we don't need to worry about that, so I'm just putting it here to show you the math. And he discovered that the solution for this equation has 2 possible energies: a positive energy, which we're used to, and a negative energy. The problem was that, well, how can we have negative energy? Surely there is a limit to how low energy of a particle can be. And he proposed that there was an anti-electron, because he was working on electrons that had same mass but a different charge than the normal electron that they were used to. And in 1933 they found it. We called it the positron, a positive electron. We learned about that in beta radiation back in topic 1 when we did nuclear physics. And from this they proposed, well, maybe all particles have an antiparticle, and so they went looking, and in 1955 they found the antiproton. And so physicists have hence concluded from this and other research that all types of matter have their own antimatter form. Important thing to note, when matter and antimatter touch, they annihilate each other into energy. You can work out how much using E equals mc squared. And back in 1999, so a long time ago for you guys, NASA gave a quote that 1 gram of anti-hydrogen would cost about $62.5 trillion to make. So it's the most expensive substance on the planet. And there's some interesting questions about matter and antimatter that you can come across in your textbook and reading. So for our definitions we need to know in terms of defining fundamental particles and antiparticles is that antimatter is a particle with an opposite charge but the same mass. So a proton instead of positive is negative, a neutron is still neutral, but it will be made of different things. Electrons, instead of being negative, are positive, and every other thing that has a charge flips to the other side. When it comes to quarks, though, there is a thing called colour. We're going to learn about that in a second. The colour also flips, so you've got to keep that in mind. There is a problem in your text, though. The text mentions that spin is flipped. Now, the problem is there are 2 types of spin. One spin is not flipped, the other spin is flipped. And the only thing that the textbook in the syllabus actually says about spin is entirely in its definition of antimatter. Now, the syllabus says antimatter is a particle that has charge and spin flipped to the opposite. However, mass is still the same. And that's it. Doesn't talk about spin anywhere else, doesn't try to define what spin is, just has it mentioned solely there once. Now, I will put an annotation on this video down in the comments section, description there, if I get some feedback back from the QCAA about whether spin will still exist. I haven't included it there because I think it should be taken off, and the only thing you need to do is just memorize this extra word to be added into the description here: opposite charge and spin, but same mass. And you can also find that in the textbook and the syllabus to write down word for word what they want you to remember. Okay, so let's have a delve into quarks. Oh, one thing of notation, in terms of writing about antimatter, we put a bar over the top of them. So here we have P for proton, oops, and P bar for an antiproton. So quarks come in 6 flavors. This is how we classify them out. When I say flavor, I don't mean chip flavors. We're not sitting there licking quarks and saying, taste salty. Okay, but maybe the scientists that discovered it were a bit bored and decided, well, we're going to call them flavors instead of types. But we're stuck with flavors. And these flavors are sorted into generations. There are 3 generations, and the generations show a pattern in the mass energy of the particle. So the 3rd generation is very, very heavy and has a lot of energy in it, while the 1st generation is very light and doesn't have that much energy into it. Now the 6 flavors you need to know, I'm just going to say them here, I'll show you the table in a moment, are up, down, charm and strange, top and bottom. You need to memorize those 6 flavors. The cognitive verb that comes from the syllabus is that you can recall the 6 flavors. But unlike protons, neutrons and electrons, there is another property that, as I said, is called color. There are 3 colors. Normal matter, like you and me, come in normal colors: red, green and blue, and the mixture of those make white. However, antimatter come with anti-red, anti-blue and anti-green. If you mix those 3 together, you also get white. You can see here that here are 3 quarks, red, green and blue, and so that's mixing together to make white, like we can see here in this color wheel. Here we have anti-blue, anti-green and anti-red, and mix them together, you would also get white. Notice that yellow is the opposite of blue. It is the anti of blue, and we've got this sort of color wheel here to help us visualize that. You don't need to understand why these colors make these things, but you do need to know that there's a green and an anti-green, a blue and an anti-blue, a red and an anti-red, and if you mix them all together, so you mix those 3 or those 3, you get white. Or in this case, it's down here, we'll talk about these in a second. If you mix red with anti-red, you get white. If you mix green with anti-green, you get white. And that tells us whether or not a particle can actually exist. So this table here, this is the table of your quarks and your anti-quarks. Okay? So you can see here we've got our generations, 1st, 2nd, 3rd. We've got our flavors, up, down, charm, strange, top, bottom. The symbols, these ones actually make sense. U for up, D for down, da 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 da. I'll skip this column for a second. Charge, red, green and blue. Over here on anti-quarks, we see that instead of an up, we've got an anti-up, and that's up with a bar over it. And the colours are red bar, green bar, blue bar for anti-colours. Now, charge. Note, quarks do not have a whole number of charge. In grade 9 we told you things can either have 1, 2, 3 positive, 1, 2, 3 negative, and that was it. We lied. Now, this is solely because we didn't know about quarks. We thought electrons were the fundamental smallest amount of charge, so they were given a 1. Now, however, we found that the quarks have less charge than a proton or electron, and these things combine to make protons, which we'll talk about in a moment. If these were found, we would have given these a +1 minus, or +2 minus 1, and then protons would be +3 and electrons would be -3, but we're not, so we're stuck with it. So note here, the up quark has a +2/3 charge, while the up anti-quark, or the anti-up quark, has a -2/3 charge. So the charge here is swapped. So you need to remember charge is swapped. but you don't need to memorize the charges. If we were expecting you to use this information, it would have to be given to you, okay? And you can see there, plus 2/3, minus 1/3, plus 2/3, minus 1/3, and we'll see some rules with these in a second. So, quarks on their own are kind of boring. We're going to stick them together. A hadron is anything where you have more than one quark stuck together. Okay, and there are two you need to know about. You need to know about mesons, and you need to know about baryons. Mesons are where you have two quarks stuck together. Baryons are where you have three quarks stuck together. There are some quarks with high numbers, 4 and 5. Like a pentaquark is the name for the 5 one. I don't know if the 4 quark has a special name because it's very, very unstable. But we don't need to know anything about those. We just need to know about the 2s and 3s. Okay. The rules for combining quarks are pretty simple, and I'll go through them just verbally, but they're not for the syllabus. Now, the charges on a quark have to add to a whole number. So if I look on here, if I was to add an up quark and a anti-up quark, well, 2/3 plus negative 2/3 would give me 0, which would be okay. It's a whole number, and it's always going to be -1, 0, or +1. If I was to add a up quark and a down quark, well, I'd only get 1/3, which is a problem. That's not a whole number. But if I added 2 up quarks and a down quark, I would get +1, which is a proton. Or if I added 2 down quarks and an up quark, I would get 0, which is a neutron. Okay, so the numbers just need to add up. So that way we need 3 from here in order to make something with a charge. If you have 1 from here, 1 from here, you're generally not going to have any charge. Although you can, I mean, if you added that's completely wrong, I shouldn't have said that. If you had an up quark with an anti-down quark, you would get a charge of +1. Okay, so where am I? So our mesons, as I said, have to have 2, and your colouring must get to white. So if you have red, green, blue, you're white. If you have anti-red, anti-blue, anti-green, you're white. That's good. If you have red and anti-red, that's white. Done. But if you had red with anti-green, that's not going to work, because red and anti-green doesn't have any green in it. This is why we have this colour property, because scientists observed that quarks had this property that they needed to sort of have the right types of quarks, even though we had flavours. So we had to have something new in order to describe these quarks, hence they chose colour. They're not actually red or green, so you're not going to be able to look at them under a microscope and go, oh yeah, it's red colour. However, there are some bonding things going on there, and so we can know that if we have quarks of our different colours, they will add up to being white, and then we know it's stable, that it can form, that's a valid particle. Note, you won't need to do anything with the colour force or the colour charges on the exam, but in my opinion it's not particularly difficult to understand. Now, what's holding these things together? Well, these are held together by the strong nuclear force. Okay, we've learned about the strong nuclear force a little bit when we did nuclear physics. So the strong nuclear force is what holds quarks together. What holds the different nucleons together is the residual strong force, which comes out of the strong nuclear force. But a lot of time, because it's just connected to it, everyone just says it's the strong force. If we go on to our mesons, well, mesons are just two quarks together, and must always be a normal quark and an anti-quark. It can't be two normal quarks. The anti-quark has to have the anti-colour, so for example it has to be red and anti-red, it has to be blue and anti-blue, green and anti-green, and remember the charge gets flipped. So if I add an up with an anti-up, we can see 2/3, negative 2/3, that's going to cancel, go to 0, that's good. 2/3, positive 1/3, it's going to go to positive 1, that's okay. Negative 1/3, negative 2/3, that's going to go to negative 1, all okay. The things involving higher generation, second and third generation quarks are generally very, very unstable, so they don't exist very quickly, but all mesons are pretty unstable, so they don't they don't hang around for very long. Okay, so mesons, you need to know they're made of 2 quarks, and you need to be able to go with all they're made of a quark and an anti-quark. That's the important part for your stuff. We're going to see some stuff with lepton and baryon numbers shortly that will be important for this. Okay, the other type of hadron is a baryon. Now, a baryon has 3 quarks. They must all be 3 normal or 3 anti-quarks. You cannot mix them. The colours will always be the 3, red, green, blue, or anti-red, anti-green, anti-blue. And again, they're stuck together using the strong nuclear force. Protons and neutrons are the most common examples, and they're very stable. Some baryons are unstable, but protons and neutrons are pretty stable. And you can see here, as I've written, a proton is made of an up-up-down, and a neutron is made of a down-down-up. While the syllabus doesn't say you need to memorise them, if you memorise that property of what a proton and a neutron is made of, it will help you with particle interactions when we get onto that topic. So I'd recommend you memorise this line here about protons and neutrons. I've just cut off the anti-quark thing just to show that, well, if we add 2 ups and a down, we got that. If we added 2 strange and two charms and a strange, again we'd get a +1. If we added 2 stranges and a charm, we'd get 0. If we added 3 strangers together, we could get to -1. That's perfectly fine. We just have to make sure that the colours, were red, green, and blue. Okay? If you added 3 up quarks together, you'd get a +2 charge, which I don't believe is valid. I would actually have to double check that. It could possibly happen, but I don't believe it can. So there's something that you could research and tell me. But again, all you really need to know is that a baryon is defined as something that's made of 3 quarks, and that that's it. That there's nothing else there that you can, because the cognitive verb is to define. So if you define a baryon is a subatomic hadron, is a particle that belongs to the hadron family that is made of 3 different quarks. It could be matter, it could be antimatter. Okay? So far in talking about all these things and these quarks, we've come to protons and neutrons, but we haven't talked about electrons. Electrons belong to a different family called the lepton. Now, quarks combine to make other particles. Leptons do not combine, so that is their big difference. Leptons come in 3 generations as well, but they are always a pair of a particle and a neutrino. And when you think back to beta decay, we've seen this word before. Okay? Generation 1 is the electron and the electron neutrino. Generation 2 is the muon and the muon neutrino. Generation 3 is the tau and the tau neutrino. Note, neutrinos are always given the symbol nu here, that weird sort of curvy letter V, and you can see VE, V mu, V tau. The muon is symbol M, the tau is symbol T, and the electron is symbol E. They are all negatively charged. The antimatter versions, though, are all positively charged. Like with quarks, 2nd and 3rd generation stuff is a lot more unstable, and so they generally will decay down to 1st generation things. We saw muons a little bit in special relativity, remember, as part of the evidence for how we know special relativity is a thing, and so that's why this is so unstable, because it's got too much energy, it just wants to decay down. You need to memorise parts of this table, especially the symbol stuff, because those symbols will get used down the track. But in terms of leptons, there's not a huge amount of information that you need to know. You need to know the 6, you need to know the names, and you should recognise their symbols and recognise their charge. Note, neutrinos have 0 charge. So, in this lesson, we've done the following things. We have explained the difference between matter and antimatter. Remember that antimatter has a different charge and spin. We've identified our 6 quarks, up, down, charm, strange, top and bottom. There are some cool stories about why they're called that. Have a look at that. Look that up. And that they combine into mesons, 2 quarks, and baryons, 3 quarks. We've identified the 6 leptons, the electron, that's a neutrino, the muon, that's neutrino, and the tau, and its neutrino. For your entrance slip to class, can you please access the O-Book and download chapter 13.1, and I'd like you to complete questions 1 to 9. You will copy the answers into the 2.3.1 space on eLearn, so that will be under topic 3. Okay? Thanks for listening, guys. Have a great evening.